Hi there. So today we are going to continue with our trig identities and trig formulas. We'll end this week with solving trig equations. So there's just sort of a few helpful identities and formulas that we'll use before we get to solving these trig equations. So this lesson is for the double angle and the half angle formulas. And so when I talk about the double angle formulas, I'm talking about sine of 2x, cosine of 2x, and tan of 2x. So the double angle, so sort of this input value there, we know represents an angle. So what I did was I went ahead and I separated 2x as x plus x. And knowing what I know about our sum and difference formulas from last week, I know that sine of alpha plus beta is equal to sine of alpha cosine of beta plus cosine of alpha sine of beta. So I'm just going to go ahead and do the same exact thing, but here I'm going to be working with x plus x. So I'll end up getting that sine of x times cosine of x plus cosine of x times sine of x. So I now can use my sum and difference formulas to summarize that sine of 2x is equal to 2 times, we'll start with sine, times sine of x cosine of x. So this is one of my double angle formulas. And we can go ahead and we can do the same exact thing here with cosine. So in red, I know that cosine of alpha plus beta is equal to cosine of alpha cosine of beta minus sine of alpha sine of beta. So I can come down here in blue and I'm replacing this with x plus x. So here that will give me cosine of x times cosine of x minus sine of x times sine of x, which is going to tell me that cosine of 2x is equal to cosine squared x minus sine squared x. And when we scroll down a little bit further, we can kind of see that there's quite a few ways to manipulate this based on what we know about the Pythagorean identity. So there are a few other pieces that you can gather from this. So there are a few other parts to the cosine double angle formula, and we'll see those as we move forward in just a little bit. And then lastly, my tan of 2x is tan of x plus x, and I know that tan of alpha plus beta is equal to tan of alpha plus tan of beta all over 1 minus tan of alpha times tan of beta. So I can go ahead and fill this in with x plus x, and that will give me tan of x plus tan of x all over 1 minus tan of x times tan of x, which will tell me that tan of, not squared, that tan of 2x is equal to 2 tan of x all over 1 minus tan squared of x. And so here is my tangent double angle formula. So that's just sort of where these come from. So again, we're building upon our previous knowledge from week to week. So we're using the sum and difference formulas that we used last week to build these double angle formulas, and we can do something a little similar with the half angle formulas. So here is the cosine double angle formula that we derived, and then these are the other two that I was talking about, how you can sort of manipulate that a little bit. These are the half angle formulas. So I'll let you go ahead and you can either read in your book and figure out sort of where these come from. Something really important though is when we evaluate, the signs of them depend on which quadrant they lie in. So let's dive into doing some of these problems here. So here I have 2 cosine of x plus sine of 2x equals 0. And you'll notice that I sort of put my double angle formulas. You'll want to have those out in front of you as you're completing this homework assignment. So when it says solve, I know that I want to get x alone on one side all by itself. So what I'm looking to do here is I have 0 on one side, 2 cosine x plus sine of 2x on the other side. So I can see here that I have a piece that's sort of involving my double angle formula. I just want to rewrite this equation, but using my double angle. So I can call this 2 cosine of x plus, and I know that's sine of 2x, so plus 2 sine of x cosine of x is equal to 0. And now I can sort of think algebraically, what can I do here? I can factor out a 2 cosine of x from both of these pieces, and I'm left with 1 plus sine of x equals 0. So now I know that either this must equal 0 or this piece must equal 0. So 2 cosine of x equals 0 and 1 plus sine of x is equal to 0. So here I can divide both sides by 2 and get that cosine of x is equal to 0, which I know happens at pi over 2 and at 3 pi over 2. So x is equal to pi over 2 and 3 pi over 2. And over here, I can subtract 1 from both sides. Sine of x is equal to -1. And I know that this happens when x is equal to 3 pi over 2. So here we have these. And so if we are, so this is kind of nicely tying into our solving of trig equations. So from here down, aside from not using the identity, we're really just solving this equation. So I know that I have because it doesn't specify the domain that these exist on, and when I say these, I mean these answers, because it doesn't specify, this could be pi over 2, it could be 7 pi over 2, so there are lots of sort of rotations around the unit circle that we could make here. So we say that we have a general solution where x is equal to pi over 2 plus 2n pi. So this 2n pi means n can be sort of any integer, and we can just keep adding 2 pi, so multiples of 2 pi. So this is the general solution for saying, well, at any sort of value or rotation around that unit circle, this is when 2 cosine of x plus sine of 2x will be equal to 0. And so we can do the same for the other piece. So x is equal to 3 pi over 2, again, plus 2n pi. And so this here is my final answer to this problem. So pretty hefty. Sort of going back, our first step was we used our double angle formulas to substitute, and then we solved this like we would solve a regular equation or one of those identities. Except a big difference between solving and an identity is that we only work on one side of the equation at a time. So let's keep moving forward to do a few more of these problems. So here we have evaluate, so sine 2 theta, cosine 2 theta, and tan 2 theta if cosine of theta is equal to 5 over 13. And it's giving me sort of a quadrant, so this is telling me that this is in quadrant 4, that this sort of piece here is in quadrant 4. So I know quadrant 4 is telling me that over here I have cosine of theta is going to be an angle that's down here. And I know that this is going to be 5/13. And knowing what I know about right triangles, I know that this side is going to be -12. So let's take a look here. Here's the angle that I'm looking at. So cosine of theta is 5/13. So let's find sine of 2 theta, cosine of 2 theta, and tan of 2 theta. Well, I know that sine of 2 theta is going to be equal to 2 sine of theta cosine of theta. So that's going to give me 2 times sine of this angle is going to be -12/13. And cosine of this angle, I already know, is 5/13. So evaluating this out, I get that sine of 2 theta is -120/169. So here's sine of 2 theta. And cosine of 2 theta is going to give me, let's see here, let's use 2 cosine squared of theta minus 1, which will yield here 2 times 25/169 minus 1, which is going to go ahead and give me -119/169. So here is cosine of 2 theta. And lastly, tan of 2 theta. So here I'll just make myself sort of a little more space. Tan of 2 theta is going to be 2 times tan of theta all over 1 minus tan squared of theta. And tangent of this triangle is going to go ahead and be, if this is the angle that we're talking about, we can say that tangent is going to give me, looking at this right triangle, looking at this coordinate point right here, I can say 2 times, let's see, -12/5. So opposite over adjacent, so 2 -12/5 all over 1 minus -12/5 all squared. And that is going to leave me with, let's see, 120 all over 119. And another way that we could approach tan of 2 theta is that we could say that this is sine of 2 theta over cosine of 2 theta. So I could take my sine of 2 theta, and I'm going to make myself a little bit more space over here. I could take my sine of 2 theta, which was -120/169, all over -119/169, and that would give me my 120/119 for my tan of 2 theta. Great. And lastly, let's just do an example together working with these half angle formulas, just so you can get one down in your notes. It says find the exact value of sine of 105. So the first thing that we want to think is that 105 is not a nice angle on our unit circle. But we do know that 105 is 210 divided by 2. So I know that sine of 210 divided by 2 is going to give me plus or minus the square root of 1 minus cosine. And you'll notice this u matches over here, so I'm looking for cosine of 210 all over 2. And then we can go ahead and we can evaluate here. So I have plus or minus 1 minus cosine of 210, is going to give me negative square root of 3 all over 2, all over 2. So we can go ahead and call this our plus plus, and this, doing out some of this algebra, will give me 2 plus the square root of 3 all over 2. And you'll notice that going from this step to this step, thinking about sine of 105, knowing that this angle, when we're talking about 105, lies in the second quadrant right here. So we're talking about the second quadrant. I know that sine is positive there, so I'm only looking for a positive answer. So this is the exact value of sine of 105. So you can take a look at the homework for the double angle and the half angle formulas, and I would certainly suggest having this page out in front of you. If you'd like to go ahead and take a screenshot of this right now, I would suggest doing that and making sure that you get these down in your notes. So double angle and half angle formulas. Good luck with the homework, guys.